Hello everyone, I'm Minghui Xie from Tsinghua University. Today I will introduce our work, PET-PS, supporting huge embedding models with persistent memory. This is a joint work with Kuaishou. As one type of deep learning model, embedding models are widely used in the core commercial business of modern web companies, including recommendation, advertisement, and searching. In these scenarios, the input features usually involve massive high-dimensional sparse features, such as user IDs, video IDs, and other ID-type features. Traditional deep learning models perform well in learning dense inputs, but do not support learning on such high-dimensional sparse feature IDs because of dimensional disaster. To overcome this, embedding models add a shim layer between the high-dimensional sparse ID and the traditional DNN, which we call the embedding layer. The embedding layer contains multiple embedding tables, such as the user embedding table and the video embedding table. Each table maps a type of high-dimensional sparse IDs to low-dimensional dense vectors, called embedding vectors. The lookup on each embedding table is similar to a query on hash table. We use IDs as keys and get the values as the embedding vectors. All embedding vectors are pooled and then fed into the traditional DNN. Modern embedding models in production environments contain up to trillions of parameters. Most of them come from the embedding tables, while the DNN part is very small, only about GB level. To serve such models, the production serving system follows a hybrid parallel architecture. For the embedding part, it is stored in multiple PSs in shards with model parallelism. For the DNN part, it is replicated in each inference server with data parallelism. Each inference server pulls the required embedding parameters based on the IDs of the current batch, and each PS consists of two components, a hash index and a memory pool. For an incoming request with a batch of IDs, PSs first get the addresses of the corresponding embedding parameters and then gather them together to do serialization and reply back to the inference server. In this work, we focus on the storage on the PS side. A common belief is that more parameters tend to bring higher model accuracy. Recently, the parameter capacity of model embedding models has grown at a rate of 10 times per year, and now has reached the hundred of trillions level. This trend makes the problem of DRAM PS become prominent. On one hand, it causes high storage costs. At Kuaishou, tens of thousands of dedicated PSs cause both high capex and opex. On the other hand, it takes considerable recovery time. When PS outages, it takes 3 minutes to load a 2 TB checkpoint from HDFS, which may violate SLA. As an emerging memory medium, persistent memory may change the landscape of PS design, with both new opportunities and challenges. For the opportunities, PM enjoys more capacity at a lower cost compared with DRAM, and its persistence can achieve a quick recovery when outages. For the challenges, PM read latency is about 3 times higher, which may affect the SLA of PS. On the other hand, by substituting DRAM with PM, the memory capacity of a single PS can expand by 8 times. This means that we have to serve more parameters requests on a slower medium, but with the same amount of CPU resources, leading to CPU bottlenecks. We build a PS using the existing PM hash index, and find that, first, as the number of client threads increases, the PS throughput is quickly bottlenecked by the CPU. Second, we break down CPU cycles and find that both indexing and gathering consume a lot of CPU cycles. Based on the background we described, we present our design of PM-based PS, PET-PS. PET-PS redesigns the indexing and gathering steps respectively. For indexing, we propose PET-hash, a PM hash index which invariants the embedding workload characteristics to minimize PM accesses to reduce the impact of PM high latency on PS performance. For gathering, we propose NIC gathering, which utilizes the scatter-gather DMA feature of commodity NICs to offload the CPU serialization process and reduce CPU bottleneck. Next, we introduce design 1 of PET-PS, PET-hash. We find that existing PM hash indexes are unaware of embedding workloads, thus losing many optimization opportunities. For example, existing indexes mostly optimize writes, where 98% of the embedding loads are read. Then, they assume frequent rehashing, where PS load is usually stable. Lastly, they assume that an operation will only have a single read or write, while a single request in PS usually contains 15 reads or writes. Thus, our observation is that index can be redesigned to minimize PM excesses by embracing the unique workload characteristic of embedding models. The first workload characteristic is the stable load of PS, which eliminates rehashing. Many prior PM hash indexes commonly adopt the multi-level structure for ease of rehashing, but pay the cost of multiple PM reads for locating one slot. Instead, PET-hash uses a single-level structure, with the advantage that we can locate any slot in O1 time without multiple reads. PET-hash consists of a single layer of buckets, and we define the first touched bucket of a certain KV is called the home bucket. When the home bucket is full, it will probe subsequent buckets. The details of read-write operations and concurrency control are not covered due to time constraints. Please check our paper if you are interested. The second characteristic is that there are usually hotspots in PS access. Thus, we design a hotness-aware migration mechanism. Its key idea is to try to swap hot KVs to their home buckets, and thus it can minimize the probing of hotspots KVs. Though the key idea is simple, concurrency control must be handled carefully. For example, during the migration process, when the reader probes to the center, and now the hot KV is migrated to the front, it may make the reader miss the key. Details can be found in our paper. The third load characteristic that can be exploited is that a request of PS usually contains a large batch of reads. And here we take a simple but efficient technique, prefetching. Specifically, when indexing the ith KV of a request, we prefetch the home bucket of the i+1th KV in this batch. In this way, combined with our hotness-aware migration technique, there is a high probability that the indexing of the next KV will be satisfied in the CPU cache or on DIMM buffer of PM. Next, we go to the second design of PET-PS, NIC gathering. We found that the existing CPU gather-based scheme wastes lots of CPU cycles, as shown in the right animation. The CPU needs to gather the embeddings on PM one by one serially, and the high PM read latency is completely exposed to the CPU pipeline. Our key observation is that commodity NICs have the scatter-gather DMA, SGDMA functionality, which can be repurposed for gathering parameters on PM. Specifically, the CPU sends a SGDMA descriptor to the NIC, filled with multiple source addresses, destination addresses, and lengths. NIC can then perform gathering or scattering, and this work mainly leverages gathering DMA. We compare CPU gathering and NIC gathering in this animation. In NIC gathering, the CPU only needs to initiate SGDMA, while gathering is offloaded to NIC. From the perspective of CPU timeline, NIC gathering eliminates PM read latency out of the CPU pipeline, thus obtaining higher PS throughput. However, we should maintain consistency when DMA embeddings. As shown in this figure, if there are concurrent writes to parameters being DMA'd, it may cause parameter inconsistency. To protect parameter consistency, we use a combination of the copy-on-write mechanism and our proposed epoch list-based space recombination scheme to ensure no write or free operations to parameters under DMA. Details can be found in our paper. In evaluation, we use a server with 1.5 TB interopting PM. We use two workloads, a synthetic workload YCSB with Z-band distribution, and a production workload collected from one major video recommendation service in Kuaishou. Both workloads run a model with 100 billion parameters. The embedding dimension is set to 128. We mainly compare PET-PS with three PS systems. PS Lite is the implementation of classic PSs in MXNet. Dash PS replaces PS Lite's index with the state-of-the-art PM hash index, Dash. KuaiPS is Kuaishou's in-house implementation of DRAM PSs. This slide shows the end-to-end performance of different PS systems. Compared to other PSs, PET-PS can get up to 1.7 times throughput improvement, with 3 times median and tail latency reduction. The right figure shows the contributions of techniques to the final performance. We begin with Dash PS. By substituting the index to PET hash, PET-PS gets up to 1.3 times, 1.5 times, and 1.7 times improvement in terms of throughput, median latency, and tail latency. With NIC gathering, it delivers up to 1.2 times higher throughput, 2.3 lower median latency, and up to 2 times lower tail latency, mainly coming from lifting the burden of gathering off the CPUs. This slide shows the performance of PET-hash. PET-hash can get 1.3 to 2.5 times throughput gains compared with previous PM indexes. We also show the average read bytes per operation. PET-hash can reduce PM read bytes by up to 2 times. We then report the performance of NIC gathering. The left figure shows the CPU time of two gathering schemes, and the right figure shows the end-to-end throughput and latency. We can see that with NIC gathering, CPU gathering time is reduced by 12.8 times, and the end-to-end throughput enhances by 1.2 times. The median latency is also reduced by 2.3 times. We also run the same experiment on DRAM. Interestingly, we found that NIC gathering instead causes a 30% decline of throughput. The underlying reason we found is that the low latency of DRAM makes the DMA engine become a performance bottleneck. To illustrate this phenomenon, we run a micro benchmark. The x-axis represents the time interval between two gathers, while the y-axis represents the throughput of gathers. As DMA are initiated to NIC more frequently, the throughput of NIC gathering quickly saturated. In PS, the indexing time is roughly the interval between two gathers. So, we also annotated the indexing time on PM and DRAM respectively, and they are on each side of the cross point. That's why NIC gathering works on PM instead of DRAM. In this figure, we run KuaiPS on DRAM and compare it with PET-PS on PM. We found that PET-PS can achieve similar latency with only 12% reduction in throughput performance. According to our internal cost estimation, PET-PS can save 13% of TCO compared to the original DRAM PS. To sum up, in the era of large-scale models, PM brings both opportunities and challenges to the design of PSs. Our proposed PET-PS redesigns indexing and gathering to tackle the challenges of PM-based PS. PET-PS brings two takeaways. First, with a good system design, PM-PS can get similar latency as DRAM PS, with much better cost efficiency. Second, NIC gathering is not free lunch. It can only be effective in some scenarios. Thank you for listening. PET-PS is open sourced in GitHub. This concludes the presentation, and I am available for questions.